Okay. Well, good morning, everyone. I was very much hoping to be with you in L'Aquila today, but current circumstances and challenges have prevented me from making it to you. So I'm going to take a little bit of the opportunity of being the first speaker of the conference to talk a little bit about the background to the hydride superconductivity and the role of a few early people in that area. But I'll finish off, I think, very much in the theme of the conference of talking a little bit about how machine learning will accelerate and improve our at least theoretical hunt for hydride materials. So this is a plot that many of you will have seen, and I'm sure we'll see many times this week. It's taken from the annual review that I wrote with Ion and Michael Eremets a few years ago, and you can see it's a little bit out of date compared to the advances that Lilia alluded to in her introduction. But it really does show that there's been a change in the field of superconductivity since around the mid 2015 or beyond, where these conventional high pressure hydrides have taken the crown of the highest TC superconductors, albeit at very high pressures. Now we should note that the previous record actually was set at high pressure at 30 gigapascal. It's sort of the last gasp of the cuprates in terms of the TC that they reached. So it wasn't completely out of nowhere that pressure played a large role in reaching these extremely high pressures, but was very much due to the special situation of dense hydrides. So let's say something about the unconventional superconductivity and why we are not doing what we're doing now with unconventional superconductors. Of course, we'd very much like to, and it's good to see that there's going to be some discussion in this workshop as to whether we might want to bring in some other pairing mechanisms to enhance TC further. But frankly, at the moment, we're not in the same position for unconventional superconductivity as we are for conventional superconductivity. Now, of course, experiment can be happily done for these unconventional systems. And in fact, they are done and used to discover novel unconventional superconductors. We can, using structure prediction techniques, to some extent, predict the structures of, say, the complex cuprates, although they do tend to be quite complex transition metal oxide structures, which are a challenge for density functional theory, and also typically involve quite a large number of atoms compared to and types of atoms compared to those that we're looking at for the hydride superconductors. But one thing that's definitely missing is a theory for these high TC, the high TC of these unconventional superconductors. Now, more strictly, the problem is not so much there not being a theory, that there's really too many theories. And also, they're not in a form that can be implemented in a first principles way, at least not in a widely available form. So if someone gives me a crystal structure, there's no computer code that I'm aware of that I could feed that structure into and obtain a reasonably accurate predicted TC if the superconductivity is unconventional. I'd be very happy to learn otherwise, and I think that would spark a massive revolution in the field. I think we'll find many of the tricks that we're using now for the conventional superconductors rapidly applied to the unconventional superconductors. So it'd be fantastic if that could be provided, but so far that's lacking. Now, what gave conventional superconductivity was very much put to one side in the history of superconductivity. It was not thought to be able to achieve very high superconducting transition temperatures, but this was really challenged by Neil Ashcroft, and I think we'll probably hear quite a lot of mention of Neil in this work, and I'm sure he'd love to have been at this workshop and contributed so much to the early stages of this work. And I just really want to highlight the key interventions Neil made that has led us to where we are with the hydrides today. So his first contribution was the famous suggestion that if we could make metallic hydrogen, it would be a high temperature superconductor. Now, this was a completely, this was not a quantitative prediction. It was very much based on simple arguments. The simple argument being really that the hydrogens are very light, and so the Debye temperatures would be very large. So for this very simple expression for TC at the top, assuming some reasonable electron-phonon coupling and density of states at the Fermi surfaces, he anticipated that hydrogen, metallic hydrogen, would have a high TC. Now, having waited from 1968 until the early 2000s, he obviously got a little bit impatient with waiting for the experimentalists to make metallic hydrogen. There have been, we're probably getting very close to that now, and in fact, indeed, there have been several reports of metallic hydrogen being formed, and its superconducting properties are being investigated, but it's certainly taking a long time to get there. So Neil thought of other approaches to achieve this sort of same end result. And so his idea proposed in 2004 was this of chemical precompression. So he used the chemical bonding in the in a system to effectively place hydrogen under higher pressure than it would be otherwise. But again, this time was in 2004. It was a sort of general manifesto of a suggestion as to what might be tried. It should be noted at this point that Neil was focusing at high pressure, high hydrogen content materials. And there actually had been a phase earlier on in the history of superconductivity where people had looked at ambient condition hydrides following Neil's metallic hydrogen suggestion. Many hydrides had been explored experimentally at low pressures, looking for superconductivity. So we haven't just, we didn't just straight leap to high pressure. It was tried at low pressure first without any particularly great success. A few superconducting systems, but nothing particularly revolutionary there. So the real change here was Neil suggesting we look at high hydrogen content compounds at high pressure. And then in 2006, he, along with with Roel Hoffman, made a concrete proposal of what might be mixed with hydrogen to make a high temperature superconductor. They suggested silane at megabar pressures. They suggested particular crystal structures that might be tested. They evaluated the electronic structure and made suggestions of what the TCs might be. Now, we'll come to this later, but there was another revolution in 2006, and that was the rise of first principle structure prediction. So Artem Oganov published his evolutionary algorithms for the USPEX method for predicting crystal structures, and at the same time, I presented the random structure searching approach, which I'll say a little bit more about shortly. And indeed, silane will be a bit of a thread of this talk. I'll mention that actually the silane result, this suggestion of Neil and Roel, was the impetus for me to publish my my structure prediction method. In fact, the first application, and I'll say a few words about that later on. But now let's just reflect on the situation we are for conventional superconductivity. Now we really have three pillars that our field are relying on. Lilia mentioned that this pillar of machine learning, artificial intelligence, is emerging as well. But I would say that these are the three solid pillars that our methods currently rest on. So experiments, of course, the high pressure community, although it's challenging, are able to do megabar diamond anvil cell experiments and measure some of the important superconductivity properties. So these compounds can be synthesized in the diamond anvil cells using laser heating and special combinations of reactants that can deliver high hydrogen contents. It's now become routine to predict crystal structures. Certainly, it's routine to predict crystal structures of the complexity that we could then go on to compute TC. Now, and the other pillar that we're resting on are these density functional perturbation theory methods for computing the electron-phonon coupling properties of realistic crystals, and from that using various approximations to compute TC. And I show the Macmillan equation below, the ingredients being the log averaged frequencies and the electron-phonon coupling constant We still have a somewhat free parameter, the mu star, there as well, but we've seen the community seems to have settled around a sort of a range of acceptable parameters that we can use for guessing TC. Alternative formulae are the Allen-Dines formula, which is substantially better. But really now, given our computational power, we should probably just be solving at least the isotropic Elie-Ashberg equations when we put all this computational effort into computing the electron-phonon coupling. We may as well use a little bit of compute to properly estimate the TC using the Elie-Ashberg method. So with these are the three pillars that allow us to get hunting, as it were, computationally for superconductors, hydrides or otherwise. So here's another plot of superconducting transition temperature with pressure. This time, particularly focusing on the hydrides. This is another plot from the Annual Reviews article, again from 2019. So it's a little bit out of date. And there are a few features that I want to point out on this plot. So the blue dots are theoretically proposed superconductors, and the yellow hexagons are those that have been confirmed experimentally. And the first thing to note is that there are, especially amongst the hydrides, there are very few. There's a few more than on this plot now, but there are relatively very few experimentally confirmed hydride superconductors. And so that's something that I hope is part of the discussion that goes on this week, in that we are currently wildly over predicting superconductivity. It's almost as if this may be a bit harsh, but it's almost as if the theoretical community is playing the lottery, throwing out predictions and hoping that theirs are the one that get found experimentally with fame and fortune that follows on. And I think that's not really acceptable. And I saw this in Nelia's suggestions for the discussion. I think we really need to be putting a little bit more effort into refining our predictions and only really presenting them as firm predictions if we're really confident that they are going to be superconductors and likely to be accessible experimentally. So the other thing to point out here is that there's this contour plot which plots the S value of these superconductors. Now, this is something I introduced when I was writing this review with Ion and Mikhail, in that I'd become worried that the TC alone was becoming the figure of merit that the community was hunting after. And you can see that if we followed that route as a community, we'd end up with very large number of predictions at very high pressure of high TCs. And frankly, as you go to higher and higher pressure, although it may be a fundamental interest to see how high a TC it is possible to obtain, it becomes more and more difficult to achieve experimentally, and obviously less and less technologically relevant. So I just wanted to introduce a new figure of merit that would steer the community towards where we really want to be, which is ambient conditions, high temperature superconductivity. And so how was it? I was sitting on a plane when I wrote this, and it's just a stab of what a figure of merit might look like, benchmarked against MGB2. So I decided that MGB2 would be 1. This very good conventional superconductor at ambient conditions. It's set so that MGB2 is 1, and so according to this figure of merit, if you have a number of higher than 1, you're doing better than MGB2, and if it's lower than 1, you're doing worse than MGB2. And so you can see that the highest values of S are achieved by these cuprate superconductors, and the hydride superconductors that have been confirmed experimentally are only really doing a little bit better than MGB2. And I think this kind of makes sense from the level of excitement that is raised outside our relatively narrow field. So I think MGB2 itself was a Nature paper. It didn't change the world. It's a useful superconducting material. There's been maybe a little bit more buzz around these superconducting hydrides, especially with the CSH result room temperature, but it really doesn't compare to the revolution of the cuprate superconductors. And so in order to reach there, we really need to be getting, S's above 3. Okay, so what that means is getting down to, say, 10 GPa with 200 Kelvin superconductivity. Now, indeed, it's actually very exciting. I mean, I wrote this. We wrote this in 2019, and I'm not sure. Not sure I can claim credit because it's pretty obvious to the top people in the field that low pressure was important, but there certainly has been a reorientation of our efforts towards lower and lower pressure. And very recently, from groups like Daifang Duan and Lilia Bori and Yangming Ma, who we're going to hear from later on, there are some very exciting results of higher TCs being achieved at lower pressures. So just to say a few words about the sort of the leg of our field that I had some role in constructing, and that's structure prediction. I'm not going to talk in detail about structure prediction. We have several people speaking this week. We use different methods of structure prediction, and they all basically work. They've been proven to work. They've predicted materials that have been subsequently discovered experimentally. They're all based on some sort of stochastic exploration of the first principles or density functional theory energy landscape. My approach is called ab initio random structure searching, and it really is a high throughput approach to structure prediction, except instead of generating your initial structures from a database of previously known or substituted structures, such as the Material Project or other similar projects do, our initial structures are randomly generated. Okay, they're randomly generated with roughly the right density, so roughly the right number of atoms in a unit cell of roughly the right volume. And maybe we don't put the atoms exactly on top of each other because density functional theory doesn't always like atoms on top of each other. But once we randomly generate these structures, we move the atoms to their nearest low energy configurations due to the forces on the atoms and the stresses on the cell. And the key thing is we do it many times until, for the systems of interest, we essentially saturate the low energy region of the energy landscape. So what do I mean by that? I mean that the structures that are low energy and therefore relevant are being found multiple times in this stochastic search. So going back a little bit, so as I mentioned earlier, that the first application of AIRS or random structure searching was actually to the superconducting hydrides. So I had been working on the structure prediction for several years. Previously, had mostly been interested in materials, so ambient condition systems, which are harder in some ways than the high pressure systems. But Richard Needs, a collaborator in Cambridge at the time, suggested actually this might be very, very useful for high pressure studies. And in fact, prior to 2006, we'd been working for some time on the hydrogen system, on high pressure hydrogen, which is a classic problem of high pressure physics. And that while that project was ongoing, Neil Ashcroft's paper in Physical Review Letters arrived. In those days, as it was a paper copy of the journal, so the paper copy of the journal arrived on the coffee table, and Richard and I happened to be drinking coffee together while we were leafing through the PRL, and we just had a look at Neil's paper, and we thought those structures are probably wrong, because they had used chemical intuition to construct these structures by hand. They had no reason particularly to think that the structures they had suggested for their superconducting hydrides were even close to the global minima. So we thought this would be an excellent test of these first principles searching methods. So pretty much that afternoon, I decided to do a few searches for silane at the pressures that they'd been exploring, the megabar pressures. And immediately, with relatively few samples, these calculations were not even done on supercomputers. They were just done on the local PCs that were available. We started finding much more stable and rather nice structures, an example of which is shown here. And this structure indeed was semiconducting, which slightly reduced dramatically reduced the chances of it being superconducting. But indeed, we did find higher pressure structures that were metallic and therefore had a chance of superconductivity. Now, this silane structure was then fairly rapidly identified in experiments that Mikhail Eremets had done. He obviously also was inspired by Neil's paper and went off and did the silane experiment, and they found exactly this structure. So this actually started the connection between the experimentalists like Mikhail and the structure prediction people like myself, Yang Ming, and Artem Oganov, where we started to talk to each other and believe each other's contributions. And it's maybe worth remembering that would not have been the case a few years earlier. I mean, the theorists were not in the habit of making structure predictions that were borne out, certainly of fairly complex structures that were borne out by experiments. So this was a mini revolution in itself. So encouraged by this silane result, I went on and explored aluminium hydride. This was my sort of first proper suggestion of a potential high temperature superconductor. It's a very interesting structure, aluminium hydride. It's a widely known hydrogen storage candidate material. It's got a very interesting electronic structure in that the density of states at the Fermi surface increases as you decrease the pressure. So that could be should it be superconducting, you maybe would be getting higher TCs as you came to lower pressures. At the same time, experimentalists, Alex Goncharov and collaborators were working on this system. Unbeknownst to either of us, we were working on the same system. And basically, at the same time we published, our theoretical predictions and their experimental results. Now, unfortunately, although later calculations showed that their early calculations showed that aluminium hydride should be a high TC superconductor, it proved not to be the case, and Ion Area and others showed that this was due to anharmonicity. So it effectively destroyed the superconductivity. So I'd say at that point I became, not exactly disillusioned, but I went off and did other things. We published the hydrogen work. I explored the possibilities of very high hydrogen content, so for example lithium compounds. But I put this superconducting hydrides business on the back burner. Unfortunately, the next two speakers and a few others didn't stop, and particularly Yang Ming Ma kept going and made some very dramatic predictions a little later on and I'm sure we'll hear a lot more about those later in the week. My subsequent efforts in superconducting hydride predictions really have been through collaboration with Dei Fang and Yang Ming and some others. And so I won't say much about that. I don't want to steal their thunder. But this was more recently. We've taken a fresh look at this problem. 10 years, over 10 years have passed since structure prediction came along, and in fact, we can now be even more ambitious than we were before. So where in the early calculations we would do a structure prediction for a single stoichiometry. In 2020, Alice Shipley and Michael Hutchin and myself decided to take a sort of more aggressive approach and do structure prediction for the whole periodic table of binary hydrides, using airs as a starting point, and then doing high throughput, i.e. many high temperatures TC computations. And the way it worked was in the following. So we took a range of different pressures up to 500 GPa, and then we did a airs search where we used what's known as saddle point airs, where we're forcing the structures to be high symmetry structures in the hope that maybe these are structures that are stabilized by dynamical effects. It has another impact in that these structures are high symmetry by definition, by construction, and therefore might be faster to compute the TC of. So it's so computing TC of low symmetry monoclinic complex structures is a slow and arduous task, and you probably don't want to do this for a large number of calculations. But we made the guess that maybe the important superconductors, and certainly based on the observations of the LAH10 and the H3S, were likely to be high symmetry in some way. So we focus our attention on high symmetry and modest number of atoms in the unit cell structures. And we were able to do those searches across the periodic table. So hydrogen plus every other element in the periodic table. So we'd compute those structures. We'd compute the convex hulls for each of those different binary pairs. In the first pass, so in the first pass we might generate upwards to heading up to 100,000 structures at each different pressure. We would remove those structures which are highly unstable. We'd also remove those structures that didn't have that had a gap, the insulating structures. We would also use a fairly simple machine learning model to guess whether those structures were likely to have a high TC or not. And so this was a model constructed by Alice, which was basically a Gaussian process regression method, which was initiated with data that was already obtained from the literature, and using quantities such as the Gasperi-Gioffre numbers, the density of states at the Fermi surface due to the hydrogens, and so on. These were the descriptors that we fed in. We'd use that Gaussian process model to pick out the structures that we thought might have a high TC, and then Michael, with a highly optimized and parallelized version of Quantum Espresso, would compute, say, tens of TCs for the remaining structures, and then we'd feed those results back into our Gaussian process model and go around in a few loops. And so this meant, we were, for each pressure, we were calculating, tens of the TC for tens of different structures. And so this was the result we ended up with. We have these red dots for predictions from our searches. And well, what you can see is that the TC, say at 500 GPa, goes up quite high. I mean, this might be maybe called hot superconductivity. But also what was really striking for us was that the maximum TC that we were finding at each pressure wasn't dropping off too quickly. It was still up in the above 200s at 100 GPa. And this actually is extremely promising. And I think it seems to be being borne out by the more detailed calculations at 50 GPa and lower by Lilia and Defang and Yangming and others. And the hydrides, although it's not clear whether we can achieve room temperature with the hydrides at ambient conditions, it seems that we can get down to pretty low pressures while we're still benefiting from this chemical preconditioning, pre-compression idea of Neil. So here's just a table. This is just a table from the paper, really just pointing out that there are several structures. The underlying structures are structures that, as far as we are aware, were new to the study that we made. So we were, rather than publishing, we were hoping to move the field from looking at one structure per paper. I mean, that's a pretty expensive way, a lot of peer review involved, a lot of writing of papers and so on, to try and do these calculations in bulk and look at many structures at once. And indeed, we're finding many novel structures with really rather high TC. We also, of course, discovered, for example, this calcium H6. A lot of the known structures just came back as well, which is reassuring. You'd like to see that in any high throughput method. So now, just to say that was the binary systems. What are we looking at now? Well, like many other people, we're looking at ternary systems. So here's just an example of a ternary. This isn't for superconductivity, just an example of the kind of systems that we're looking at in my group, the ternary systems. This was looking for new carbonate materials for carbon capture. So there's other pressing concerns other than superconductivity. So we're trying to see what we can do to help with the climate change situation. And indeed, we uncovered some novel carbonates in titanium carbonate and aluminium carbonate that had kind of interesting energetics for carbon capture. But the real point is here, we are able to do these structural predictions over a wide range of different compositions. And here's another example with Andreas Hermann and Lewis Conway, where at high pressure, we're looking at quaternary systems, the hydrogen, carbon, nitrogen, oxygen system. Now, these are expensive calculations. You need to generate hundreds of thousands of structures to look at this ternary space, and maybe even that isn't enough, but it is becoming possible now. So here's some example of some unpublished results in the superconductivity area. I generated 112 different 112 ternary convex hulls for the ABH system, where A is a list of elements including magnesium, yttrium, lanthanum, and so on, and B includes lithium, beryllium, the light elements. So we probably think we want to have some metallic element, some light elements, and hydrogen. So what hasn't been completed so far is the computing of the TC for these compositions. The first thing is to generate these convex hulls en masse or in a high throughput way. So now the final topic, and I'm eventually going to come back to silane again, is a new trend in structure prediction, and I suspect we'll hear more of it. I'm sure I saw it very much. The roadmap that Lilia put together had this as a very strong theme, and that's that if we use these new generation of machine learning potentials, we can possibly dramatically accelerate structure prediction. Now, there are many machine learning potentials that are out there. They're in fact rather easy to construct. So it's not surprising that there's been a proliferation of these machine learning machine learning potentials. I decided to add yet another one to the machine learning, to the stable of machine learning potentials. In that I wanted to design one that was basically precisely for random structure searching, so precisely for the kind of searches that I want to do, rather than repurposing potentials that we use for other things. So many of the machine learning potentials that are constructed have a particular focus on extending length scales and time scales. So they're designed so that you can do larger systems for longer times in a molecular dynamics simulation. But molecular dynamics is very different to random structure search. In molecular dynamics, you're largely moving around, say, the bottom of valleys in an energy landscape, whereas random search, you're putting the atoms in really crazy positions, atoms nearly on top of each other and so on. And so it's a real challenge for the standard machine learning potentials. So the first step here was to recognize that when you're doing a random structure search, you put constraints on your search that restrict you to certain subregions of the configuration space. So, for example, these light blue regions. And so what I wanted to do is make potentials that were designed for precisely the subspaces that the search was going to be performed in. So I call these are bespoke potentials. And in the end, I call them ephemeral potentials, because the idea is that you make a potential for a particular search, you do the search, and then you do another search, you make another potential. So these are not sort of preciously built potentials that you want to hand on from group to group to use for any particular purpose. You just want to make one in half an hour or so, use it, and then move on to another one. So the key requirements of these potentials is they've got to be fast, they've got to be simple and robust. So I've come up with I think probably as simple as you could, a multi-body representation for our potentials that go in to produce this descriptor. So for the two-body terms, they're just a function raised to a power, and your descriptor is the choice of several of these different powers and summed over the other species in the other atoms around your atom. A similar thing for the three-body terms, but it's just a product of three of these functions raised to two different powers. And this is chosen so that you have the correct permutational symmetry, and this can be extended to four-body terms. Now, this function that we used, when I started out, it was essentially the 1 over R function that we would get from a Lennard-Jones style potential, but eventually I settled on this simple piecewise linear term. So just a function that goes from 2 at 0 and 0 at 2 and passes through 1 halfway through. And as you raise it to different powers, you generate these different functions. They're also based on
5 minutes.
Okay, thank you. They're also based on neural networks. In fact, multiple very small neural networks. So these are forget deep learning. This is shallow, narrow learning. So these are very narrow neural networks and very shallow, but we make many of them and we train them just directly. We don't use stochastic gradients descents. We use Levenberg-Marquardt iteratively reweighted least squares. And then we combine them in a very special way. We combine them using non-negative least squares. And what non-negative least squares means is that the weighting in front of each neural network is either 0 or a small positive number. It's essentially a sparse combination of these many neural networks, and by many I mean maybe thousands. So we essentially do airs or random structure search with the neural networks. We make 1,000 of them, and then we combine them together in this non-negative least squares way, and that selects maybe only 20 of the neural networks that are useful. The potentials are trained iteratively, so we start by making very random structures. Okay, this is important because we need to get some reasonable description of the high energy region of the landscape. And then we go on to iteratively add extra terms. So we do airs, random structure searching with the first generation of potential, find some structures which may be bad, but recompute the DFT energies for those structures, shaken a little bit to the new the region of that landscape. And then we just go around in a loop a few times. This helps eliminate the sort of the pathological regions of the potential. So if the potential wants to go somewhere that's a bad place, we'll calculate the DFT energy, it will raise the energy, and then in the next iteration, the potential won't want to go there anymore. And so here's an example of showing what sort of a predicted versus true energy might look like for these potentials. So this is a 4-species potential. It's not a superconducting hydride. This is an oxalate. We're looking at this for battery cathode materials. But what you can see is that you can see fairly bad agreement for these high energy regions of the landscape. And that's sort of what we want. We don't want the potential to take the high energy regions of the landscape too seriously, but we do want those regions to have high energies. And then as you move to the low energy bit, you get very good matching between the theoretical and the experimental and the computed, the predicted and the computed energies. So putting all that together, I revisited the silane result. I was looking. Before I published this approach, I wanted to make sure I could do something I couldn't do otherwise, or at least hadn't done otherwise. So I revisited the silane result, and with making an iteratively generating a potential at 300, or actually I think it was 500 GPa, I was then able to do a search with hundreds of thousands of samples. So these potentials are potentially tens of thousands of times faster than computing DFT. So you can do many more, you can compute many more structures in much larger systems. And I was excited and somewhat amazed to find that in silane, which is a system that I'd studied, Artem Oganov had studied, and other groups, the Jilin group had also studied in depth using evolutionary algorithms, random search over a decade or so, that there were still things to find. And indeed, I found this rather complex 60-atom primitive unit cell structure of silane, which is gives this red curve here in the enthalpy plot, which is considerably more stable than the others that had been found with purely first principles methods. And what's more, when you compute the density of states of these structures, it has a much lower density of states. So I think this tells us maybe a couple of things, that probably, although it's been common to say that the searches, the binary hydrides have been explored, I would suggest that we probably should have another look at those. I think we're probably missing things, and probably missing some of the more complex structures. Now, of course, that's a bit of a challenge because these complex structures are harder to compute the TC of. But actually, this might explain some of the over-prediction of TC in this field. That many of the structures that will have been proposed to be superconducting may well be maybe more metastable than people realize and not accessible in experiment. And the other thing to point out is that it's a feature of this field is that if you get into this field and you don't do a brilliant job at structure prediction, you're likely to find more high TC superconductors. Okay, it's just the nature tries. The better, more relaxed structures tend to have lower density of states at the Fermi surface and are more stable in some way. Whereas the unstable structures maybe have higher electron phonon coupling, they're closer to an instability, and maybe have high density of states. So there's a little bit of a strange bias in the field. So I think certainly we should look at the overprediction in some detail. Okay, so just to wrap up now, so the change now compared to 10 years ago is that we can compute TC for very large numbers of systems in one go. If you do better searches, I think you'll probably have fewer superconductors, which might explain the over prediction. And something I'd like to bring to the discussion, the theory discussion at least, is we're really going to start to need to put together our results and have databases so we don't end up redoing things that people have done before. It can be quite hard to tell if you've got something genuinely new or someone has already done this now. So that's me done.